Hi everyone, this is lecture video 17 and we will explain linearization and differentials in this lecture video. So look at these figures as the first thing. You will see the curve y equals x squared and the tangent line to our curve at the point x equals 1 here, right? So this is our curve. Y equals x squared, and the pink one is the tangent line to y equals x curve, at which point x equals 1, you see. So we want to zoom in to this tangency point. Okay, let's write this down. Zoom in to this point. Okay. This point, once you zoom in, you will see this kind of picture. Zoom in more, you will obtain this display, and if you zoom in more, you will see this display in your screen. So what do you notice? What happens when we zoom in? As long as we zoom in, or the more we zoom in, the less difference we obtain between the curve and the tangent line. And if you continue this process, zooming in process, you will eventually find out that at the tangency point, the curve and the tangent line get so closer, and then eventually they behave like the same. Okay, let me write this down. At the tangency point, the curve, the function, and the tangent line are so close to each other . And we can say that they are almost the same with a very small error. Okay, so we will use this idea to approximate the value of the functions at some particular point. We can approximate the value of the function by looking at the value at the tangent line, and you see they are almost the same. So this kind of idea can be used to approximate the value of functions. The values of the function and the values on the tangent line are so close to each other. Values of the function, values on the tangent line. So let's use this idea, use this information to construct linearization function. Okay, so again, we have this curve. Our curve is y equals f of x. We draw this tangent line, and its slope is given with this quantity. And then you can write the equation of this tangent line, right? Tangent line is written y minus y0, which is given as f of a. This is the point x0 and this is the point y0 on our curve. Then on the right side, the slope is given as the first derivative of the function at this point a times x minus x0. This gives us the equation of the tangent line, and as we observe that at some point near your tangency point, let's say this one, the values of your function, which is here, and the values on the tangent line are so close to each other. That's why we will use the values on the tangent line to approximate the values on the curve. And to be able to express this approximation, we will solve for the values on the tangent line from this equation. So solve for y here. These are the values on the tangent line. Tangent line. So y is what? F prime of a, x minus a plus f of a. And let me rewrite this function by taking f of a in front, f prime of a, x minus a. And from now on, we will name this function as the linearization of f at the point x equals a, okay? Now I am defining linearization function as the same as the values on the tangent line. So this function is the definition of what? Definition of the linearization function of f of x at x equals a. So we will define the linearization function like this. What is the importance of the linearization function? The importance comes from the fact that the values of the linearization function, which is the same as the tangent line, are so close to the actual values of our function. So we will use linearization to approximate the original values of our function. Use linearization function to approximate the values of your original function. Okay, let's move on. Once you understand the importance, we can start solving examples on the linearization function, which is given by this equation. Okay, the same thing is explained here. This is the formal statement taken from your course book, and this is the importance of your linearization function. Okay, let's move on. So this is our first example. We will be dealing with this function. F of x is square root 1 plus x. And we want to find the linearization of it at this particular point. So we will choose a here in the expression as 0, okay? And the same story applies here. At this point, you draw this tangent line. This is the tangent line. And if you zoom in to this square, you will see that the pink tangent line and the blue curve are so close to each other around the tangency point. The pink one is the tangent curve, the blue one is the curve, original curve, and around the tangency point, the values of them are so close. That's why we are using the linearization values to approximate the original values of the function. So let's create the linearization function for this particular example. The formula for it comes from the values on the tangent line. So we are using the tangent line equation here. So a is given as 0 in the statement, x minus a, which is 0. Okay, so our function has an explicit expression, 1 plus x. So what is the first derivative function then? 1 over 2 times square root of 1 plus x. That's why the first derivative function at 0 is what? Insert 0 for x, it is 1/2. What is the original function's value at 0? It is 1. Then you are ready to insert those values here. This is 1, this is computed as 1/2, and here you just have x. So this gives you the value of the expression for the linearization function. L of x is computed as 1 plus x over 2, just like given here. So 1 plus x over 2, this is the linearization function that we computed here. Now, this diagram shows you the exact value of the function, which is square root 1 plus x, and the values computed by the linearization function. So this is the exact value of your function at the point 0.2, this and this. So f of 0.2 is square root of 1.2, obviously. And you know that f of x is approximately the same as the L of x function. So let's compute the value of this square root expression from L of x. So insert 0.2 here, so you obtain this. And if by using the calculator, you can compute the exact value of the square root, and it is computed like that. And you can do these computations for other values too, like f of 0.05, f of 0.005. This is the value coming from the linearization function. This is the original value computed by calculators. And if you compare them, you see that they are approximately the same with a very small error. Okay, so next example. Now, our function is cosine x, and we want to find the linearization function at x equals pi over 2. So it goes like f pi over 2, f prime pi over 2, x minus pi over 2. For the point A, I inserted pi over 2. If your function is cosine x function, then the first derivative is minus sine x. So minus sine x function evaluated at pi over 2 is minus 1. And what is f of pi over 2? Cosine pi over 2, which is 0. Okay, let's insert this information here. F of pi over 2 is computed as 0. This is computed as minus 1. Okay, so minus 1 times x minus pi over 2. That's why the linearization function is minus x plus pi over 2. Okay. And the crucial fact here is that you can use this linearization function to approximate the values of your original function. Okay, cosine x function is almost the same as this linear function. Okay, let's move on with the next example. Find the values of this strange expression approximately. So here, to approximate the values of this power thing, you can use this function, right? Okay, so we want to approximate the values of this function at the point x equals 0.9, we will find the linearization of it. Find linearization of the given function f of x at which point? Here, for the tangency point, so for the point of A that we discussed above, you will choose some particular point, right, to create your linearization function. And while you are choosing this point, you will take the nearest integer to x value given there, okay? Take the closest integer. Choose the closest integer to draw your tangent line. Okay, let's choose 1 in this case. Okay, now I am ready to create the linearization function of f of x at the point 1. So it goes like f of 1 plus f prime of 1 x minus 1. So what is f of 1? Here, if you insert 1 here, you will find 1. What is f prime of x? You know, you need to use logarithmic differentiation here, which is explained in one of the previous lecture videos. By using logarithmic differentiations, you will find the first derivative as this one here. I am skipping the details. And let's evaluate this first derivative at the point 1. It gives us, I think, 1. Okay, so this is computed as 1, this is computed as 1, and the linearization function becomes L of x is 1 plus x minus 1, so it is just x. So what we understand here? We understand that f of x is approximately the same as L of x, which is given by just x. So we want to find the values of f 0.9, right? Because what is your f? X to the power x, and if you insert x equals 0.9, you find exactly this quantity, and approximately this quantity is same as the value of the linearization function at the same point, like this. So, you know, computing linearization function is much more simpler than the computing this power function, which is impossible by hand. If you have a calculator, you can easily compute this, but manually, you can approximate the result of this power evaluation by using linearization function just like this, very quickly, you know. So this value is approximately 0.9 by using the linearization function. I stop here. See you in the next lecture video.